Thank you everyone for coming to my talk. I'm Jianhan, a PhD student with the EC department of UT Austin. Today I'm going to talk about our paper, Online Learning for Hierarchical Scheduling to Support Network Slicing in Cellular Networks. This is a joint work with my supervisors, Professor Gustavo de Viciana and Professor Sanjay Shakotai. Let me first start with the general idea of network slicing. Basically, it's a hierarchical framework for resource allocation. The base station first maps users or the traffic flows into several slices. Then it partitions network resources, the bandwidth for example, into those virtual slices based on some allocation rule. This allocation typically happens in a slow timescale. At the same time, base station deploys flow-level schedulers within slices, which schedule users using resources allocated to each slice by the slice-level scheduler. This is fast timescale allocation, and some opportunistic schedulers which use the instantaneous channel and queue information can be applied in this level, like the max wait scheduler or log rule scheduler. There are various motivations for slicing. For instance, people may want groups of users under different service providers isolated from each other in the presence of traffic load variations, like in the MVNO service model. It may also be a reasonable choice to group flows based on similar quality of service requirements. So, network slicing is a very useful model with many practical uses, and with no doubt it has gained more and more attention in the recent decades. Here we introduce a general model of the hierarchical structure which we consider in our paper. We assume stochastic packet arrivals for traffic flows, each associated with a queue. And each user experiences random channels as well, which can be observed by the base station. Compared to a classical scheduling model, in network slicing, users first group into S slices, or say S groups. There is a slice-level scheduler, which allocates resources to slices based on some allocation parameter. We call it the weight W. Proper slice-level scheduler can be GPS, the generalized processor sharing, which allocates resources to busy slices proportional to this weight vector. Then we also have flow-level schedulers for every slice. They are pre-selected opportunistic schedulers scheduling users using queue and channel information. And the whole hierarchical scheduler consists of both slice and flow-level schedulers. The way to evaluate this scheduling scheme depends on how we define the utility or rewards. There can be various rewards in application, like minimizing mean delay or rewarding packets to meet specific deadline constraints. In our paper, we do not restrict ourselves to any specific reward scheme, and we want to solve the following general question. What is the best slice-level allocation with respect to the current reward model? In other words, what is the optimal W? With no doubt, this problem is analytically hard to solve due to its complexity. For example, it depends on the traffic and channel conditions, how you do the slicing, what flow-level scheduler you deploy, etc. So what can we do here? We apply a bandit perspective. Our approach is to model the problem as a black box optimization. We consider the rewards of the system are accumulated over time, and for each allocation vector W, there is a corresponding rate of rewards under the current scheduling and reward model, which we call FW. The ground truth function F and the optimal weight W star, as this picture shows, are unknown to the scheduler in advance due to the complexity of this model. But we can always choose different weights W to run the scheduler and collect feedback, and then try to get an estimation over the function FW. In other words, we are using a bandit. The arms are the weights W, while the feedbacks are how good this hierarchical scheduler performs under different W. So here we go. We have two main challenges when applying this bandit perspective. First, in queuing system, rewards collected are typically queue dependent. For example, if the rewards are delay related, then having long queues typically means the utility is low at the moment. That means we can't just pull a new arm, choose a new weight, say every 10 seconds, and collect feedback. We may choose a good weight, but the reward feedback is skewed by a previous bad weight choice leading to a long queue. In other words, the feedback samples will not be conditionally independent given the weight vector W. To solve this problem, we operate our bandit algorithm at a new timescale, the queuing cycles, and instead of optimizing the average reward, our algorithm optimizes the ratio of rewards or cycles. The second challenge is that we have infinitely many arms, or say weight choices, over a continuous set. So instead of using classical bandit algorithm designed for discrete arms like ETC or UCB, we will apply the optimistic tree search approach, but on the timescale of random cycles. We will discuss the two challenges respectively in the following slides. First, let's describe this system dynamics using cycles. This picture illustrates how a queuing system alternates between idle period, which means empty queues, and busy periods. And an idle period plus a busy period is a cycle. Each cycle is associated with a random length and a random reward accrued over its time. And we have the conditional independence here. Under appropriate assumptions on traffic and reward models, we consider the length and reward variables are independent across cycles for any fixed weight W. This is essential for the comparison of different arms. Under this independence assumption, we can apply the fact that the empirical estimate of the rate of rewards FW equals the cycle reward average over the cycle length average using only the W-induced cycles. So this suggests that we should use a single weight for a full cycle and collect feedback for the estimation of F. But what if a cycle never ends? This will happen if we accidentally explore a weight that indeed destabilizes the queuing system. For example, if the weight we select does not fulfill the throughput of one of the slices, then the queues will grow and the cycle will never end. To avoid this situation, we adopt a clipping mechanism. This means when a cycle is too long, we allow the packets currently in the system being discarded and force the start of a new cycle. Accordingly, we define the clipping threshold. A cycle is clipped if it exceeds its threshold. However, since the cycle length of any stable weight is random and indeed it's a sub-exponential variable, there is a small probability a cycle induced by a good stable weight can also be clipped for any fixed threshold. So we design the threshold to be logarithmically grow over cycle index, and this ensures stable weights eventually not getting clipped. Meanwhile, those unstable weights are penalized when clipped and rarely played after some initial exploration. And in the analysis, we can show that this clipping will not affect the regret guarantee overall. This figure illustrates how we operate the bandit. When a cycle starts, we choose a weight W, and we only change the weight when a new cycle begins. When a cycle is too long, we clip the cycle based on the clipping threshold and switch to a new weight. At the end of the cycle, we collect the random feedback, which includes the cycle length and reward information. The second challenge of our bandit, as we previously discussed, is the continuous set of arms. We use the tree search approach. To find the optimal solution, we first partition the weight space into a binary tree, as this picture shows. Then the general idea is as follows. We first build an estimation tree for the function f corresponding to the binary tree. This means for each node of the tree, we'd like to give an estimation regarding the function f using its corresponding feedback samples. Therefore, the deeper the tree, the better is the estimation as long as we have enough samples. Based on this estimation tree, we can choose weights from partitions with good estimates. And because more samples are collected from the partition with good feedback, the estimation tree is grown deeper from there and ideally towards the optimal solution. This approach assumes some proper smoothness on the function f, which is true in our setting, and it uses the fact that closed arms induce similar feedback. That's why it's useful for a continuous set of arms. Here as a side note, being optimistic means underexplored partitions are compensated in terms of estimation score to encourage exploration. Now we will give a brief overview of our algorithm. We call it the cycle-based HOO with clipping, or CHOOK. It follows the line of research on optimistic tree search, which goes back to the UCT paper, followed by zooming, HOO, and many more recent variants. Our CHOOK algorithm is a modified HOO algorithm, adaptive to random queuing cycles and clipping. As in classical optimistic tree search, we first create hierarchical partitions over the weight space W as a binary tree. Then we dynamically assign scores to partitions using corresponding feedback. The score equals the empirical reward average over empirical cycle average, plus an exploration bonus, which is used to ensure the score is sufficiently optimistic. At the same time, for each cycle, we exploit samples, choose weights from partitions with best scores. Due to the time limit, I will not discuss the details of the algorithm. The main technical difficulty is the design of a proper exploration bonus, which involves dealing with the double stochasticity of both reward and cycle variables and the scenario of unstable queues that need to be clipped. Please refer to the paper for detail. To summarize the whole CHOOK framework, in the outer step here, the black box optimization step, we apply a CHOOK algorithm for weight selection and the estimation update for function f. Then in the inner step, we generate samples by running the hierarchical scheduler with random length cycles plus clipping. For analytical purpose, we compute the upper bound of the regret induced by our CHOOK algorithm. The regret is the loss of reward with respect to the optimal choice. We show a sublinear regret which has the same order of HOO regret despite random cycles and clipping. Again, we leave the details to the paper. Finally, we will present one of our simulation results to exhibit the convergence behavior of our CHOOK framework. We set up a simulation system following the parameters from an urban macrocell deployment guideline. In this experiment, we assume 12 users are grouped into 2 slices served by 1 base station. Slice 1 users' rewards are minimizing mean delay, while slice 2 users' rewards are meeting strict packet deadlines. We apply GPS as the slice level scheduler and log rule as the flow level schedulers for both slices. So here are the results. In the top left figure, this blue curve is the ground truth f obtained by simulating every weight vector in advance, and the optimal weight distribution is around 0.4, 0.6. Then I apply CHOOK. The 3 figures below are the explored tree over time with CHOOK. Here, each dot represents a sample. The x-axis is its corresponding weight value, and the y-axis represents which depth of the tree this sample belongs to. As you can see, after 2000 cycles, most of the weight samples already concentrate around the optimal solution. As more cycles are collected, the tree further grows towards the optimal weight. And finally, we plot the regret over time, and it exhibits a sublinear growth as we expected. Please refer to our paper for more experiment results. In summary, in our paper, we parameterize the hierarchical scheduling model for network slicing by a weight vector and formulate as an online black box optimization problem. Then we introduce a bandit algorithm for online parameter selection, the chook. It is an optimistic tree search algorithm built from HOO with modifications to account for queuing cycles with clippings. To apply chook, the scheduler adaptively chooses weight vectors based on bandit feedback of previous cycles on a timescale of cycles. Finally, our framework is verified by a couple of simulation experiments. So that's all for my presentation. Thanks for your time.